Welcome back, everyone. I hope you guys were able to watch 15.1 and 15.2. We're going to go over 15.3 and 15.4 and 15.5, which covers thermochemical equations, calculating enthalpy change, and reaction spontaneity. So make sure that you guys have a piece of paper, something to write with, and possibly your textbook if you need a little bit more help. If you do not have that yet, pause the video now, go grab that stuff, and I'll be right here. Being that you guys have that stuff now, let's go right into thermochemical equations. So the objectives are going to be right here if you guys want to read them, and a review of the vocab. And here's some new vocab words. Remember, you can pause, rewind, or go forward in this video anytime that you feel like if you need more time on different sections. So taking a look at specifically writing thermochemical equations. A thermochemical equation is a balanced chemical equation that includes the physical states of all reactants and products and energy change. Then there's also the enthalpy or heat of combustion of a substance, which is the enthalpy change of the complete burning of 1 mole of a substance. That is a specific value for whenever you're dealing with combustion, like in the demo that I gave you guys. Now, here's a specific table where you can see different combustions, the delta H's of different combustions. So like sucrose, octane, glucose, propane, and methane. You do not need to memorize these. However, you'll probably be provided these values in, let's say, a test or something like that. Now, changes of state. So when you're dealing with delta H, you can deal with delta H within a specific state of matter. However, when you're changing from one state to another, there's a different value that you're going to be using. Let's say specifically between going from a liquid to a gas, you're going to use the molar enthalpy of vaporization. It refers to how much energy is required to vaporize 1 mole of a liquid substance. And then you have, for going from a solid to a liquid, you have the heat of fusion, which is the same concept, but 1 mole of a solid substance to a liquid. Now, here's a couple of standard enthalpies that you should be aware of, but what you should know is the vaporization and fusion of water. So you have 40.7 kilojoules for every mole. That's how much energy it takes in order to essentially go from a liquid to a gas of water. Same thing for fusion, going from a solid to a liquid, 6.01 kilojoules for every mole. Now here's a look at it in the enthalpy chart. So you can see between the different states of matter that you have the specific values, like for fusion down here and for vaporization. Combustion is a reaction of a fuel with an oxygen. You guys already do know that. And food can be one of those options. So at this point, I'm going to take a look to see what you guys know. So the amount of energy required to melt 1 mole of a solid is called what? Pause now if you need more time. Alright, so you guys should have already gotten this. It is molar enthalpy of fusion, going from a solid to a liquid. And how about this one? A thermochemical equation specifies amount changes in what? Should be enthalpy, right? Alright, so that's going to be at a 15.3. If you need to pause and take a break, do that now. I will be right here. Being as you guys are ready, we're going to move on to 15.4. 15.4 deals with specifically the application of calculating enthalpy change. So how can we apply Hess's law? What is Hess's law? That's what we're going to kind of be looking at in this section. So here's some new vocab words that you guys should have already gotten down for your vocabulary. And let's look particularly at what Hess's law states. So it states that if you can add two or more thermochemical equations to produce a final equation for a reaction, then the sum of the enthalpy changes for the individual reactions will be the summation of the change for the final reaction. How does that work? Well, we'll look at that right here. So, we have our starting reaction of sulfur and oxygen. So sulfur and oxygen combine together to sulfur dioxide, and it releases into the system around negative 594 kilojoules. So it releases that. Now, we have that sulfur dioxide. We're going to combine that with more oxygen. And that sulfur dioxide and oxygen are going to combine together to create sulfur trioxide. And that's going to release even more energy into the system. So if you were to add those two up together, that's going to be your overall energy change, going from sulfur and oxygen to sulfur trioxide. Now, looking at the heat of formation, what is the heat of formation? It's defined as the change in enthalpy that accompanies the formation of 1 mole of a compound in its standard state from the elements in their standard states. Now, this can trick some people up because elements in their standard states have a delta F naught of 0.0 kilojoules. That you need to know. So let's say O2, N2, H2, Fe, S, they all have 0 kilojoules as their standard state. Now, in order to form the compounds, these are typically placed above or below elements in their standard states. And we can take a look at that on a chart coming up. So for example, in this chart, we have nitrogen, oxygen, and sulfur are in their standard state. In order to form nitrogen dioxide, energy has to be added into the system in order to form nitrogen dioxide. That's why it's a positive. Energy can be released from the system if you have the formation of sulfur trioxide. That's the example right down here. So every single one's going to be unique. Now, there's more on the heat of formation. So standard enthalpies of formation can be used to calculate the enthalpies for many reactions under standard conditions by using Hess's law. Now, how is this done? Well, you got to use the summation equation. You got the delta H naught of the reaction equals the summation, or sigma, of delta H naught final, so the products, and the summation of delta H naught final of the reactants. That is basically combining multiple standard states all together. If you're confused by this, that's fine. We'll have time in class to cover this. And just bring your questions in. So here's a chart of looking at some other standard enthalpies of formation. So going with H2S, HF, SO3, SF6. Those are just a couple examples. Now, let's assess what you guys already know. So what is the enthalpy of oxygen in its standard state? Pause now if you need more time. You guys should have gotten 0. Remember, standard state, always 0. Standard state, always 0. Get that into your brain. Standard state, always 0. Standard state, always 0. Great way to memorize it. Now let's try this one. 2 or more thermochemical reactions can be summed to determine the overall enthalpy changes based on what law? Pause now if you need more time. If you guys got this wrong, I'd be very shocked because 2 of these deal with gases and the other one deals with energy in whole. So, if you figured out what I'm talking about, you should have gotten Hess's law. Now that's going to end 15.4 here. If you need to pause and take a break, hit the pause button, come right back. I'll be right here. For those of you that are ready to go, let's move on to the last section of 15.5, spontaneity. So these are just going to be the objectives that we're going to be covering here for spontaneity. And here's some new vocab words. You guys should have already got these down. Alright. So, what is a spontaneous process? Well, it is a physical or chemical change that once begun occurs with no outside intervention. That is once it occurs. Doesn't matter if something starts it. It's just once it does start, nothing will intervene. So with this, most spontaneous processes require some energy from the surrounding in order to start that process. Great example, rolling a ball down a hill. So you're all the way at the top and you push the ball just barely so that it starts rolling, and it's going to roll and roll and roll all the way down to the bottom of the hill. Now, gravity takes a hold of that. That's the same kind of concept with this. It's like gravity, pulling it down, keep getting it to the lowest amount of energy it's going to have, releasing all that energy. And that also connects to entropy. What exactly is entropy? Well, it is the measure of the possible ways that the energy of a system can be distributed. And this is related to specifically the freedom of the system's particles to move around in a number of ways that are different arrangements. So I have a great example on this slide right here where we've got oxygen on one side and helium on the other. And currently the valve is closed. But once we open that valve, there's 4 different possibilities here because of this dual chamber environment. Now, what's specific about these? Well, let's take a look at that. So the second law of thermodynamics states that spontaneous processes always proceed in such a way that entropy of the universe increases. That is a must know. You have to know that. Entropy is sometimes considered a measure of disorder and randomness of the particles in a system. So the more random something is, the higher the entropy. Just like that. More disorder, more spread out, higher entropy. That's why you think gases have a higher disorder than solids do. So enthalpy changes associated with changes in state can be predicted. So entropy increases as the substance changes from a solid to a liquid and then a liquid to a gas, as I mentioned before. Now, however, if you dissolve a gas into a liquid to form a solution, the entropy of the system will be decreased because that gas that's moving around the air is now in a defined volume in the liquid. Now, on the other hand, assuming no change in physical state occurs, the entropy of the system usually increases when the number of gaseous particles is greater than that of the gaseous reactant particles. That's dealing with a combustion reaction or other reactions that deal with 2 sets of gases. If you have more moles of gases on the right-hand side of the equation, your entropy is going to be a lot higher because there's more molecules there. However, there are some exceptions with entropy increasing whenever a solid, a liquid, is dissolved in a solvent. So that may occur where you have some that have a decrease in entropy, but most of the time you're going to have an increase in entropy. And the random motion of particles of a substance increases as the temperature increases. That is a standard based on how much kinetic energy each molecule has. So the more energy it has, the higher the temperature. It kind of goes hand in hand with that. Let's look at entropy of the universe and free energy. So in nature, when entropy tends to be positive whenever the reaction of the process is exothermic, which raises the temperature of the surroundings, the entropy of the system increases. Free energy is specifically the energy that's available to do work. Now, what is this? Well, we can look at Gibbs free energy equation. And that is delta G system equals delta H of the system minus T delta S of the system. We'll get into each of these in just a second. So you guys already know what T is. You already know what delta H is. We'll get into what delta S is in just a second. If the sign of energy change, delta G naught, is positive, the reaction is non-spontaneous. If the sign of the energy is negative, it is spontaneous. So positive, not spontaneous. Negative is spontaneous. The entropy of the universe, which is the system plus the surroundings, always increases in any spontaneous process. So you can take a look at this chart and you can see how this equation compares depending on the delta H of the system, the delta S of the system, the delta G of the system, and what the reaction spontaneity would be. Now, if you guys want to play around with the concepts in motion, take a look at the PowerPoint that I have posted up on Edsby for you guys. You can look at these concepts in motion. Now, last but not least, let's take a look at assessments. So, what is the measure of randomness in a system? Pause now if you need more time. You guys should have gotten entropy. Not enthalpy, but entropy. And lastly, energy that is available to do work is what? Did you get free energy? That's what you should have gotten. Alright, so that brings us to the end of this section. If you guys want to go through this PowerPoint, go through on your own. There are different resources here for you guys that you can take a look at. And as you can see, different resources. And then if you need help at all with this, on how to understand how to use this, you can do that too. But other than that, if you have any questions, send me a message on Edsby, send me an email. You can also ask me while you're there at school. You will have a quiz walking in on Friday. Last couple of reminders. As I mentioned just now, you will have that quiz walking in on Friday. I have not created the quiz yet, but you will have probably around 5 to 6 questions. Can't guarantee that. And then you need to also have your PowerPoints ready from the energy... Sorry, lost my train of thought. The Energy Symposium. So you need to have your PowerPoints ready for that on Friday. And other than that, thank you guys for watching this. Have a great rest of your evening, and I'll see you guys on Friday.